Welcome to Ask and Learn.
Okay, well, in problem 18, we have a Carnot cycle, and we must find three different things in here. The first item, we have to find the maximum pressure of the cycle. Then item B, we have to find the input heat. And in item C, we have to find the mass and the cycle. Okay, so looking in the table A17, we can see that this cycle operates between two temperatures. So the temperature 1 is 1200 Kelvin. That gives us a relative pressure of 230, 238. That is correct? Yeah, that is correct. 238. And the temperature 2 of this Carnot cycle, which is 350 Kelvin, gives us a relative pressure 4 of 2.379. Therefore, we can conclude that the maximum pressure, is going to be between the top reservoir of the Carnot cycle, which means that that can only be pressure 1 or pressure 2. But we know that it's going to be the pressure 1 because she has the minimal volume. So it's going to be the maximum pressure. Therefore, the maximum pressure, this is really bad written, so let's do it again. The maximum pressure is going to be the P1 pressure, which is just the relative pressure divided by the relative pressure on 4 times the pressure on 4, which gives us, let's see, 238 divided by 2.379, that multiplies 300. Therefore, the maximum pressure is 30.013 megapascals. Okay, so that's the first answer to this problem. Now let's move on to the input heat. And to find the input heat, we can look to the efficiency, because the efficiency of the Carnot cycle, of any cycle actually, is just the network divided by the input heat. So this is the standard equation to find the efficiency of any thermodynamic cycle. Therefore, we have that the input heat is going to be the network divided by the efficiency. And we just need to find the Carnot efficiency, because this is our Carnot cycle. Okay, so the Carnot efficiency is defined by 1 minus Tc, actually not Tc, Tl, sorry, is the temperature of the low reservoir divided by the temperature of the high energy reservoir. And this is going to be 1 minus 350 divided by 1200, which gives us efficiency of 70.83%. This is not good. Let's rewrite this. 70.83%. Okay? Well, now that we have the efficiency, we also know the network, because the problem gives us. Therefore, the input is going to be 0.5 kilojoules divided by 7083, which gives us an input energy of 0.706 kilojoules. That's the second answer. And to calculate the mass, well, the mass is a little more complicated because we need to look to the TS diagram and remember about the variation of the entropy. So what we must know, let's see, this is going to be the mass is just the network divided by the work by the entropy. This is the network, and this is, as we know, 0.5 divided by the change in the entropy, which is S1, S2, TH minus TL is just the area inside the cycle, okay? Because just an observation, remember that a Carnot cycle on a TS diagram is represented as a square box, okay? This is the isentropic, this is the isentropic. So this omega that we are calculating here is just the area inside this box. This is just an observation for each one that we want to calculate this. So this is what we managed to calculate here. S1 minus S2 that multiplies THTL. Okay, so who is S1 minus S2? This is going to be equal n equals 0.5. We do not have S1 and S2, but we know who is S4 minus S3 minus R natural log of P4 P3. Okay, that multiplies TH minus TL. This is 0. Therefore, we can simplify this to be simply, let me see, this is going to be 0.5 divided by the change in the temperature, let's call delta T, just to simplify, that multiplies R natural log P4 P3, okay? And substituting the numerical values of these quantities, we have that the mass in this Carnot cycle is going to be equal 0.5 divided by 0.287, which is R, natural log of 300 divided by 150, that multiplies the change in the temperature, 1200 minus 350. Calculating all this, we finally find the mass equals 0.00296 kilograms. Okay, that's the final answer to this problem. Thanks for watching.